Welcome back to my channel. So in this video, we are going to continue the double integration method, uh, slope and deflection of a simply supported beam with uniformly distributed load. So what we will do, we will consider a simply supported beam AB of length L, which is loaded with a uniformly distributed load throughout the entire span of the beam, and this small w is called the rate of loading. So as usual, so we have to first calculate the reaction forces for the simply supported beam, and let us assume RA and RB as the reaction forces at the supports A and B. And when we apply our equilibrium equation, we have all the sum of vertical forces is equal to 0. So which will give RA plus RB is equal to W times L. And this W is called the rate of loading, and L is called the distance over which UDL acts. So when we multiply these two, we will get our force, which is the force due to our UDL. So again, we apply our second equilibrium equation. Sum of moments about point B is equal to 0, which is nothing but RA times L, that is force into distance, which is equal to W into L by 2, which is nothing but again a moment where W into L gives the force, rate of loading into the distance as discussed in the previous step, and L by 2 is the distance of the center of gravity from point B, which is L by 2 in case of a UDL. So when we simplify, we just get RA equal to W L by 2. So we substitute this RA is equal to WL by 2 in our equation 1. We get RB, which is also equal to WL by 2. So now we have both our reaction forces are equal as WL by 2. So as usual, again, we consider a section XX at a distance of small x from the right support B. So at this section XX, with the bending moment is nothing but M is equal to plus RB, that is WL by 2 times X, which is anti-clockwise direction. And as usual, clockwise direction we have for the UDL, which is W into X into X by 2, where X is the distance for which the loading acts and CG distance accordingly. So we apply our differential equation for the deflection of the beam, which is EI d square y by dx square is equal to M. And we substitute the M from the previous slide, that is WL by X by 2 minus W X square by 2. And let this be our equation 2. And we are going to integrate the integration the equation number 2 and find out the constant. So upon integration of the equation 2, we get EI dy by dx is equal to, so WL by 2 into integral of x will become x square by 2. And we have integral of x square as x cube by 3. So this will become minus WX cube by 6 as integral constant C1. So just simplify, you will get WL x square by 4 minus W x cube by 6 plus C1. So to evaluate the constant C1, I am going to apply the boundary condition. At mid-span, we have the slope as 0. So when x equal to L by 2, our slope dy by dx becomes 0. We just substitute this dy by dx here. And wherever x is there, we are going to put L by 2. So obviously, we get W L by 4 into x square, that is L by 2 whole square, minus W by 6 into, instead of x, we have L by 2. So L by 2 whole cube plus C1. And when we simplify this, will become L square by 4. So this will become WL cube by 16. And here you have L cube by 8. 8, 6 are 48. So you have WL cube by 48. And the left hand side will become 0. So next what we will do, we will take LCM. So we will get 3 WL cube by 48 minus WL cube by 48. That is 2 WL cube by 48. And it will become WL cube by 24. And when you bring to the other side, you have negative of the value W L cube by 24. So once you find this constant C1, put back in our slope equation, we get EI dy by dx is equal to WL x square by 4 minus WX cube by 6 minus WL cube by 24. This will be our slope equation. So once we find the slope equation, we are again going to integrate it. We get our deflection equation. Right? So we integrate the equation 4, we get EI of y is equal to WL by 4 into x square integration x cube by 3 and wx by 6. Integral x cube will become x power 4 by 4 minus WL cube by 24, and it's a constant. When you integrate, you get x value and again another constant C2. Now to find this constant C2, again I'm going to put the second boundary condition, that is at the supports our deflections are 0, therefore at x equal to 0 we have y is equal to 0. So upon substitution we get EI of 0 is equal to, wherever x is there we just put 0 and we end up at the final value of C2, which is 0. So the constant C2 gets neglected. So the remaining will become our diffraction equation, that is EI of y is equal to WL by 4 into x cube by 3 minus W by 6 x power 4 by 4 minus WL cube by 24 times x. And we simplify this as WLX cube by 12 minus WX power 4 by 24 minus WL cube x by 24. And this equation is called as the deflection equation. So the summary, we have our slope equation as well as the deflection equation. So you can substitute the value of x, which will give the slope and deflection at any point in the beam as you wish. So this concludes this video. We will meet later. Thank you.